Oxygen makes up about 1/5 of the air around you. You do not feel it entering your lungs, yet every cell waits for it. Remove it, and brain tissue begins to suffer within minutes. Every pulse in your chest depends on that unseen exchange. For most animals, it is not optional. It fuels movement, thought, warmth. The larger and more complex the body, the more is required. For centuries, biology treated this as an accepted certainty. Energy rises with oxygen, and life expands where breath remains steady. But far below the ocean's surface, there are places where that certainty begins to loosen. At certain depths, levels fall toward zero. Fish drift upward and away. Crabs turn back. Entire regions are known as dead zones. Some are widening as warming water holds less dissolved gas, reshaping ecosystems layer by layer. In deep basins sealed from circulation for thousands of years, dense water rests beneath lighter currents. The chemistry turns hostile. The temperature lingers near freezing. Pressure gathers with immense force. Most scientists assumed nothing complex could endure there. Yet when sediment cores were lifted carefully to the surface, something unexpected appeared. Not microbes, not flattened traces of the past, something multicellular, something intact, structures consistent with living tissue, no clear signs of decay. A finding that unsettled a long-standing assumption. But if oxygen has long been considered essential for animals, why do complex forms appear where it vanishes? What does their presence reveal about early Earth? When this gas was scarce and life was only beginning, how long have these isolated basins supported organisms beyond our expectations, and how far does this oxygen-free realm extend beneath the waves? Tonight, we descend slowly toward basins where breath disappears and long-held rules begin to thin. But before we begin, if you enjoy calm and soothing explorations like this one, filled with wonder, science, and the gentle unraveling of life's mysteries, I'd love it if you gave this video a gentle like and maybe tap subscribe. It helps more curious minds find their way to this peaceful little corner of the internet. And if you'd be so kind, let me know in the comments where you're winding down from tonight and what time is it there. It's always a joy to see how far across the world this little sleepy corner of science travels. Now take a deep breath, let your shoulders soften, and together let us slip beneath the surface into the depths where oxygen vanishes. Long before bones formed or fins traced slow arcs through water, the planet kept a different rhythm, one measured in minerals, tides, and faint chemical murmurs. The surface was restless, yet the air itself held almost none of the restless element, now woven into every modern metabolism. Seas carried dissolved metals, skies leaned thick with volcanic exhalations, and life, still small and soft, persisted in forms that neither sought nor required the gas that would later reshape destiny. Those earliest organisms lived by quieter exchanges. Their cells drew energy from reactions that unfolded without brightness or flame, guided by gradients in chemistry rather than any invisible current from above. Within them, ancient molecular systems passed particles along delicate chains, releasing just enough power to mend structures and divide. Nothing hurried. Time stretched wide, and existence settled into patience. Across immense ages, subtle artisans began to alter the balance. Certain microbes learned to split water using sunlight, releasing a byproduct that drifted upward and lingered. At first, this newcomer vanished as quickly as it appeared, absorbed by iron in the oceans and stone on the continents. Rusting minerals locked it away, layer upon layer, until those vast sinks grew full. Only then did the surplus begin to remain, thin at first, then slowly thickening through spans longer than mountains endure. As its presence deepened, cells encountered a substance both perilous and promising. This reactive gas could tear fragile molecules apart, yet it also offered a remarkable gift. When guided carefully within specialized compartments, it allowed fuel to be broken down far more completely. The same nutrients that once yielded a modest trickle of energy could now release a flood. With that surplus, membranes strengthened, internal scaffolding expanded, and new shapes became possible. Gradually, size ceased to be a burden. Larger forms could sustain themselves because their cells harvested more from every fragment of food. Tissues diversified, some devoted to motion, others to sensing, others to transport. Cooperation within bodies mirrored ancient cooperation among microbes, each part sustained by the generous chemistry unfolding inside microscopic chambers. Complexity unfolded not as a sudden leap, but as a long unfurling, guided by the steady availability of this potent element. Over time, dependence settled in like a habit learned too well to forget. Lineages that mastered its use flourished across land and sea, their descendants inheriting machinery tuned to its presence. In such creatures, energy and oxygen became partners, so closely linked that one seemed to define the possibility of the other. The idea took root that vitality itself was bound to that single ingredient, as if life and this gas shared a single name. Yet the deeper record of Earth, written in stone and cell alike, holds quieter verses beneath that belief. Numbers appear first, not in a laboratory, but as faint signals drifting across monitoring screens aboard research vessels. They arrive as quiet measurements from sensors lowered into open water, each value marking how much dissolved oxygen lingers at a given depth. Near the surface, the readings seem generous, yet as the instruments sink, the figures slide downward until they approach a threshold so low that gills can no longer draw what bodies require. These descending layers form vast midwater regions known as oxygen minimum zones, suspended like transparent veils within the sea. Such zones stretch across broad portions of the Pacific and the Arabian Sea, occupying depths where sunlight has faded, yet pressure has not fully claimed the water below. Within these bands, animals accustomed to steady respiration begin to falter. Fish that wander too far into the thinning layers slow their movements, their muscles starved of the chemical that keeps fibers contracting. Some turn upward in gradual retreat, while others drift in place, their strength dissolving into the surrounding dimness. The boundary is invisible, though its effects move through living tissue with quiet certainty. The causes gather far above, carried in warmth that settles over the ocean's skin. As surface temperatures rise, the water's ability to hold dissolved gases diminishes, much as warm air releases a fading scent. At the same time, heating strengthens stratification, arranging the sea into stacked layers that resist mixing. Oxygen replenished from the atmosphere remains near the top, while deeper strata grow isolated, their reserves slowly consumed by respiration and decay. What was once a modest gradient becomes a pronounced divide, shaped by physics as gentle and relentless as gravity. Over years and decades, these depleted regions broaden. Currents shift their margins, climate patterns nudge them outward, and seasonal variations linger longer than they once did. Creatures that depend on richer concentrations adjust their ranges, rising toward shallower corridors where survival still finds footing. Predators follow prey into narrower bands, compressing food webs into thinner vertical spaces. Life continues, yet its arrangement changes, as though an unseen ceiling presses gradually downward while the seafloor waits below. In certain places, the transformation has become measurable even without instruments. Fisheries note altered catch depths, and long-studied migration routes trace new arcs through the water column. Species adapted to scarcity endure where others withdraw, their metabolisms attuned to scarcity, like slow clocks that rarely need winding. Between these layers lies a delicate frontier, not a line drawn in water, but a shifting threshold defined by chemistry, where a slight change in concentration determines whether motion persists or stillness settles in. Far beneath familiar coasts, where ancient ships once crossed sunlit trade routes, the seafloor opens into hollows shaped like quiet bowls. These depressions rest beyond the reach of storms or tides, sealed by their own weight and chemistry. When exploration craft first descended into them, their lights revealed something that did not behave like ordinary seawater. The beams struck a surface that shimmered as if it were a lake suspended inside the sea, its boundaries so sharp that it reflected like glass. These were brine pools, reservoirs of water saturated with dissolved salts far beyond normal ocean levels. Their density made them sink and remain, settling into the deepest contours where they resisted blending with the surrounding layers. Instead of diffusing, they held their form, heavy and still. The separation could be seen where the two fluids met, a wavering horizon where currents slowed and particles drifted as though uncertain which realm to enter. Within these basins, circulation faded into near absence. Without mixing, the supply of dissolved oxygen dwindled long ago, consumed by chemical reactions and never restored. The trapped liquid became an isolated world, governed by different rules, its composition enriched with compounds that most organisms cannot tolerate. Sulfides and concentrated salts infused it, creating conditions that would disrupt delicate cellular machinery within moments. Yet the pools remained, unbroken and undisturbed, preserving their unusual character across spans longer than human history has recorded. Above them, ordinary seawater flowed on, unaware of what lay below. Beneath them, sediments accumulated in thin, patient layers. Each grain settled gently, untouched by burrowing creatures or shifting currents. Over centuries, the deposits formed a quiet archive, their strata aligned like pages in a sealed chronicle. Chemical signatures lingered within those layers, traces of distant climates and ancient plankton blooms, all safeguarded by the stillness that prevented disturbance. The discovery of these basins did not arrive with spectacle, only with careful observation and repeated descent. Instruments confirmed what the eyes suggested, that the fluid inside was several times saltier than the sea above it. Measurements showed no measurable oxygen, not even the faintest residue. The realization unfolded gradually, like a curtain lifting without sound, revealing an environment that had remained unchanged while civilizations rose and vanished along the shores far overhead. In that submerged quiet, time seemed to loosen its pace. Nothing stirred unless it crossed the boundary, and anything that did often sank without motion once it entered. The pools held their silence, dense and enduring, as if they had chosen stillness long ago and never found reason to release it. Gloved hands steadied the narrow cylinder as it rose from the deck cradle, its metal surface beaded with droplets drawn from great depth. Inside rested a column of sediment collected far below, a vertical slice of seafloor lifted carefully from a basin long sealed from circulating currents. The operation had been routine, one of many extractions meant to catalog microscopic inhabitants that thrive where oxygen has long since vanished. Nothing in the procedure suggested surprise, only the quiet discipline of repetition refined through years at sea. When the core was opened and its layers exposed, the material appeared undisturbed, banded in subtle shades that marked slow accumulation across centuries. Researchers leaned close beneath laboratory lights, expecting the usual signs of bacterial presence: faint films, scattered organic grains, the delicate residue of microbial existence. Instead, within the compacted grains, lay shapes that did not resemble colonies or residue. They held form, they possessed symmetry. Their outlines suggested bodies rather than traces. At first, the forms seemed like fragments carried from elsewhere, perhaps debris that had drifted downward before burial. Yet, the surrounding sediment showed no sign of turbulence, no disruption that would accompany intrusion from above. The tiny structures remained intact, not collapsed or dissolved, their surfaces defined as though time had paused around them. Under magnification, textures appeared that matched tissues rather than minerals, patterns consistent with organized anatomy rather than accident. Silence gathered around the observation table as attention shifted from casual inspection to careful verification. Instruments were adjusted, lenses cleaned, notes compared. Each new angle confirmed the same impression. These were not impressions left behind after decay. They resembled complete organisms, preserved with a delicacy that suggested recent life rather than ancient remains. The basin from which they came was known for chemistry hostile to complex cells, a place assumed to exclude such forms entirely. Discussion unfolded in low voices, cautious and deliberate. Some proposed that the specimens must have entered during retrieval, perhaps introduced by equipment or currents, unnoticed during ascent. Others considered whether dormant stages of known animals could endure conditions once thought impossible. The samples were tested for contamination, their surroundings analyzed, their composition measured against the water and mud that enclosed them. Results returned without easy resolution, each confirmation deepening the puzzle rather than settling it. Word traveled beyond the vessel to laboratories ashore, where colleagues examined images and data transmitted across cables and satellites. Interpretations diverged, though none dismissed the clarity of what had been seen. The cores rested in chilled storage, their contents unchanged, holding within their quiet layers the suggestion that a long-accepted boundary might not be as fixed as once believed. In classification charts that map the diversity of life, there exists a small and easily overlooked branch bearing a name unfamiliar even to many biologists. Within that quiet corner reside the loriciferans, organisms so minute that dozens could rest upon a grain of sand. Their bodies are enclosed in protective casings called loricae, intricate shells built from layered plates that fit together with the precision of mosaic tiles. Under magnification, these coverings reveal ridges, spines, and delicate seams, features that give each individual the appearance of a finely crafted instrument rather than a drifting creature. They were first described from ordinary marine sediments where oxygen still threaded its way between particles. There, among nematodes and other microscopic fauna, they passed unnoticed for ages, grazing on bacteria and organic fragments. Their movements were subtle, guided by rings of tiny scallods that flexed and retracted like soft bristles. Nothing about them suggested extremity. They seemed part of the familiar hidden multitude that inhabits seafloor grains across the world. Specimens recovered from the isolated basins, however, carried a different implication. The same distinctive armor, the same retractable structures, the same orderly anatomy appeared within samples taken from depths where dissolved oxygen had long been absent. Closer examination revealed individuals in multiple stages of development, some bearing eggs, others showing forms associated with growth and molting. These were not stray visitors preserved by chance. They appeared to belong there, residents rather than accidents. Microscopic imaging uncovered further details. Internal regions that in most animals house mitochondria displayed shapes more consistent with hydrogenosome-like organelles, cellular components known to function without oxygen. The arrangement suggested metabolism adapted to chemical pathways rarely associated with multicellular life. Instead of relying on the familiar cascade that ends with oxygen as final acceptor, their cells seemed prepared to complete energy reactions through alternative routes, slower yet sufficient for their modest needs. Such evidence unsettled expectations that had guided zoology for generations. Complexity had long been paired with oxygen, as though the two were inseparable companions, one sustaining the other. The presence of these armored beings within permanently anoxic sediments suggested a different relationship, one in which intricate anatomy could persist without that partnership. Their existence did not overturn established principles, yet it pressed gently against them like a tide testing the edges of a shore. Debate followed not with raised voices but with careful papers, repeated analyses, and cautious phrasing. Some researchers proposed dormant transport from oxygenated regions. Others pointed to the developmental stages as signs of a complete local cycle. As observations accumulated, the loriciferans remained unchanged, their minute forms continuing their slow lives beyond ordinary reach, carrying within their structure a quiet reminder that evolution often explores paths more varied than theory once allowed. Inside most animal cells, energy is gathered through a choreography so refined that it unfolds unnoticed, a procession of reactions passing from molecule to molecule until fuel is fully spent. At the center of this procession stand mitochondria, minute chambers where oxygen receives the final electrons and allows the entire sequence to continue. This exchange releases a generous yield of usable energy, enough to sustain motion, growth, and repair. For creatures whose tissues depend on steady supply, this process hums constantly, as essential and unobserved as a heartbeat. In the minute inhabitants of those secluded sediments, the internal landscape appears arranged differently. Close inspection of their cellular interiors has revealed bodies that resemble mitochondria in outline yet differ in structure and chemistry. These organelles show traits similar to hydrogenosomes, components known from certain single-celled organisms that thrive where oxygen never enters. Within such compartments, energy is drawn from nutrients through pathways that end not with oxygen, but with other molecules that accept the final charge. The reactions proceed quietly, releasing smaller packets of power. This altered chemistry reshapes the tempo of existence. Without the high yield that oxygen-based respiration provides, every process slows. Growth stretches across longer spans, movement becomes restrained, and activity settles into a rhythm measured in subtle shifts rather than swift motion. The cells do not strain against this pace. Their architecture suggests long adaptation, membranes and enzymes tuned to function within narrow energetic margins. Nothing is wasted, nothing hurried. Chemical traces support this portrait of restraint. Enzymatic markers associated with anaerobic metabolism appear where one would expect the usual machinery of oxygen use. Compounds produced as byproducts match those formed in pathways that rely on sulfate or organic molecules instead of oxygen as terminal partners. Each reaction releases only modest energy, yet the cumulative effect suffices for bodies so small and demands so slight. In this economy, efficiency matters more than abundance. Such physiology reveals a different strategy for survival. Rather than building systems that require constant richness, these organisms embody a design that flourishes on scarcity. Their tissues persist on limited fuel, maintaining structure and function with careful balance. Even reproduction proceeds within these constraints, suggesting that their entire life cycle unfolds according to the same quiet arithmetic. Viewed through this lens, Their existence resembles a candle burning with a very small flame, steady and enduring because it consumes so little. The chemistry within them continues its gentle circuits, sustaining life through reactions that neither blaze nor fade, but remain poised in a delicate equilibrium suited to the stillness that surrounds them. Time moves differently for organisms whose lives unfold at the edge of energy's allowance. In habitats where every chemical reaction must be carefully spent, existence stretches into a quieter tempo, as if each moment has been gently lengthened. The smallest motions take on significance, not through drama but through persistence. Cells divide at intervals so wide they resemble seasons rather than instants, and growth proceeds by increments almost too subtle to measure except across long observation. Within such conditions, movement becomes a rare gesture. Muscular effort, costly even for larger creatures in richer surroundings, would drain precious reserves here. Instead, these beings remain mostly still, their forms resting among surrounding grains, while internal processes continue their slow circulation. Nutrients that drift close are gathered with delicate structures, absorbed without haste, converted through pathways tuned for restraint. No sudden bursts disturb their rhythm. Activity exists, yet it is measured, economical, guided by the principle that survival favors balance over exertion. Their bodies reflect this philosophy of conservation. Tissues remain compact, lacking elaborate extensions that would demand constant upkeep. Cellular machinery operates at a reduced pace, enzymes folding and unfolding in sequences calibrated to minimal expenditure. Even repair follows this pattern, with molecular damage corrected gradually rather than immediately. Such patience does not weaken them. Instead, it shields them from the strain that rapid metabolism might impose in a place where fuel is scarce. Reproduction follows the same deliberate cadence. Developmental stages unfold with careful timing, each transformation completed only when sufficient resources have accumulated. Eggs mature slowly, protected within forms designed to endure long intervals before hatching. New individuals emerge already suited to the prevailing conditions, requiring little adjustment because their physiology has never known abundance. Generations overlap like faint echoes, one beginning before another has fully faded, continuity maintained through steady succession rather than sudden proliferation. This manner of life contrasts with the quickened cycles familiar in sunlit waters or on land, where growth and motion often race forward. Here, endurance depends not on speed, but on the ability to remain. By keeping demands low, these organisms avoid the risk of exhausting what little is available. Their strategy resembles a quiet negotiation with their environment, each process matched precisely to what the surroundings can provide. Seen over extended spans, such stillness reveals its own kind of dynamism. Populations persist across years without noticeable change, yet their persistence itself is a form of activity, a sustained dialogue between biology and chemistry. The result is a model of existence shaped not by competition or expansion, but by equilibrium, a way of living in which continuity is achieved through gentleness of pace and unwavering moderation. Among the most delicate clues gathered from those secluded depths were not the adults themselves, but the smaller forms resting beside them. Within the fine grains appeared ovoid structures with defined membranes, shapes consistent with eggs rather than fragments. Nearby lay individuals at differing stages of development, their proportions subtly shifting from one specimen to the next. The arrangement suggested succession, as though a quiet lineage had unfolded entirely within that isolated setting, each phase preserved in place like notes held in suspension. Chemical analyses of the surrounding material strengthened this impression. Measurements taken from the sediment layers showed no trace of oxygen penetrating downward from above. The compounds present were those stable only in its absence, signatures that would quickly alter if even small amounts entered. Such stability implied long continuity, a chemical stillness maintained across spans sufficient for many generations. In such conditions, any organism discovered intact could not easily be explained as a recent arrival from elsewhere. Yet, interpretation did not settle into certainty. Researchers studying the samples weighed each observation with deliberate care, aware that unusual findings demand patient scrutiny. Some proposed that dormant stages might endure transport before becoming active, while others pointed to the developmental variety as evidence of a complete cycle occurring in place. The specimens themselves offered no testimony beyond their form, leaving the surrounding data to speak in quiet fragments. Efforts to repeat the discovery faced practical limits imposed by the environment from which the originals came. The basins lie in regions difficult to access, and collecting undisturbed material requires equipment capable of preserving fragile layers during ascent. Even slight disturbance can alter chemical conditions, introducing traces that were never present below. Each expedition must therefore replicate not only location but technique, a task shaped by weather, depth, and the constraints of technology. Time between attempts can stretch into years, slowing the accumulation of confirming evidence. Within scientific circles, such circumstances are familiar terrain. When observations challenge established expectations, they are met first with verification, then with independent examination. Instruments are recalibrated, procedures reviewed, and interpretations compared against alternative explanations. This process unfolds gradually, not as resistance but as refinement, ensuring that conclusions rest upon foundations as steady as possible. In this measured way, knowledge grows, shaped by repetition and careful doubt alike. So the question of whether these organisms pass their entire existence within those secluded sediments remains held in thoughtful suspension. The samples rest in curated collections, their minute forms unchanged, while analysis continues in laboratories far from the depths where they were found. Evidence accumulates in increments, each addition subtle, each weighed with attention, as understanding advances with the same unhurried patience that seems to guide the lives under study. Not all creatures that dwell near oxygen's edge abandon it entirely. Some remain tied to it by thin threads, enduring concentrations so slight they resemble whispers rather than supply. In dim seafloor habitats, where circulation slows, certain worms extend slender bodies through the sediment, their tissues adapted to draw the last traces from water that would seem empty by ordinary measure. Specialized pigments within their blood bind the faint molecules with unusual efficiency, holding them long enough to sustain quiet cellular work. Nearby drift gelatinous forms whose survival depends less on extraction than on endurance. Jellyfish possess tissues built mostly from water, their structure requiring little energy to maintain. When oxygen falls, they do not struggle against the change, but simply continue at a gentler pace. Their pulses slow, their movements soften, and their metabolism adjusts until demand matches what remains available. Such resilience arises not from independence, but from flexibility, a capacity to ease their needs until scarcity no longer threatens. Among crustaceans living in similar margins, another strategy unfolds. Some species lower their internal activity when oxygen declines, entering a state akin to suspended animation. Heart rates diminish, digestion pauses, and motion ceases except for the smallest adjustments. Enzymatic reactions that would normally proceed at steady speed become measured and sparse, conserving reserves until conditions improve. When richer water returns, these animals revive, their systems accelerating once more as though a dimmed lantern had been gently brightened. These varied responses reveal a spectrum rather than a single solution. At one end stand organisms that tolerate deprivation by reducing their requirements, remaining linked to oxygen, yet able to persist when it nearly disappears. At the other rest those whose chemistry no longer depends on it at all, their internal reactions guided along different pathways. Between these poles lies a gradual transition, a continuum shaped by evolution's patient adjustments over countless generations. Physiological studies show how subtle these distinctions can be. The difference between survival and collapse may rest on the presence of a single enzyme variant or a membrane slightly altered in composition. Proteins that bind oxygen more tightly, cells that store it briefly, or tissues that function with minimal supply all extend the range an organism can inhabit. Each adaptation represents a small shift, yet together they map the boundary where reliance fades into independence. In this borderland, life demonstrates that necessity can be met through many designs. Some creatures cling to the faintest traces, others wait in stillness until abundance returns, and a few move beyond the need entirely. Their coexistence forms a quiet gradient of possibility, showing that the limits of survival are not fixed lines, but gentle transitions, drawn by chemistry and shaped by time. A drifting speck of organic debris sinks through the water column and meets a border it cannot see. One moment it falls freely, the next it slows, as if the sea itself has thickened. Below lies a pool not of separate liquid in the ordinary sense, but of seawater altered so profoundly that it behaves like a distinct world. Its salinity has risen to such extremes that it settles into depressions and remains there, gathered into basins that resemble inland lakes, though they rest beneath thousands of meters of open ocean. The boundary between these layers forms a narrow transition where chemistry shifts abruptly. Dissolved substances change concentration within a span no thicker than a hand. Above, conditions remain tolerable to wandering animals. Below, the dissolved mixture becomes hostile to most forms of complex life. Small swimmers that descend unaware may cross this invisible threshold and lose equilibrium within seconds, their physiology unprepared for the sudden alteration surrounding them. Their bodies sink gently afterward, coming to rest along the margin, like fallen leaves collecting at the edge of still water. Along that margin, however, other communities flourish. Filaments of microorganisms weave themselves into soft mats that spread across the interface, drawing energy from compounds rising out of the depths below. These microbes do not rely on sunlight or abundant oxygen. Instead, they harness chemical gradients, linking reactions together in sequences that release just enough power to sustain growth. Their colonies form pale veils and textured patches, living tapestries nourished by contrast rather than uniformity. The pools themselves remain remarkably stable. Their contents resist dilution because the surrounding water, though fluid, cannot easily mix with a solution so concentrated. This stability allows unusual combinations of dissolved minerals to persist, shaping an environment governed more by chemistry than by motion. Substances that would disperse elsewhere accumulate here, creating conditions that select only those organisms equipped with rare biochemical tolerances. In this way, the basin becomes less a place than a filter, admitting life forms suited to its particular balance while excluding nearly all others. Creatures adapted to the upper layers often skirt these boundaries without crossing them, sensing subtle changes through receptors attuned to salinity or pressure. Their paths curve gently along the perimeter, tracing the outline of the hidden lake. Meanwhile, the microbial inhabitants continue their slow work, transforming compounds molecule by molecule, sustaining a quiet ecosystem that depends not on abundance but on contrast. Such submerged reservoirs reveal how profoundly environment can shape biology. Where chemistry shifts, life reorganizes. Where conditions intensify, only certain designs endure. And within these silent basins, separated from the wider sea by gradients too fine to see, existence persists according to rules written not in light or motion, but in the invisible language of molecules. Within every living cell, countless reactions unfold in careful succession, each one passing fragments of energy along invisible routes. Under ordinary conditions, these routes converge on a final step in which electrons are handed to oxygen, a transaction that releases a substantial reserve of usable power. This concluding exchange acts like a deep reservoir at the end of a river, drawing the entire current forward and allowing earlier reactions to proceed efficiently. Because of this arrangement, nutrients can be broken down completely, their stored potential converted into the chemical currency that sustains structure and motion. When oxygen is absent, the sequence must follow different paths. The earlier stages still function, dismantling organic molecules and releasing small amounts of energy, yet the final transfer requires another partner. Some cells pass their electrons to nitrate, others to sulfate, and still others to carbon compounds. These substitutes accept the charge less readily, and the reactions they permit release far smaller returns. The difference resembles the contrast between a steep waterfall and a gentle slope, both carrying water downward yet yielding unequal force. Organisms adapted to such conditions construct their metabolism around these modest yields. Enzymes are arranged to capture every fraction of released energy, channeling it into essential tasks while discarding nothing. Chemical byproducts that would be rare elsewhere become central here, circulating through pathways tuned for efficiency rather than speed. Each molecule of fuel must serve thoroughly before it is spent, for the margin between sufficiency and depletion remains narrow. This constraint shapes physiology at every level. Cells remain small because large volumes would demand more energy than these reactions can supply. Tissues stay simple, avoiding elaborate structures whose maintenance would exceed available resources. Even internal transport slows, with substances diffusing gradually instead of being propelled through active systems. Life persists, though its pace aligns with the limited current that flows through these alternative chains. The surrounding environment often reflects the same chemistry. Sulfur compounds may accumulate, lending the water a faint mineral scent, while nitrogen derivatives circulate in quiet cycles. Microorganisms participate in these transformations, linking their own metabolisms with those of nearby animals in subtle networks of exchange. Energy moves through this community in restrained increments, passing from one form to another without ever gathering into abundance. Such existence carries a cost, measured not in hardship but in restraint. Growth remains measured, reproduction deliberate, and activity subdued. Yet within those limits, stability arises. By matching their needs to what these reactions can provide, organisms maintain a steady balance, sustained by pathways that operate without the powerful oxidizing partner common elsewhere. In that balance, life demonstrates that vitality does not always depend on intensity, but can endure through careful use of even the faintest energetic flow. Long before the atmosphere settled into its present balance, the planet wore a different chemical cloak, one that would feel unfamiliar to modern lungs. The oceans that filled its basins held almost no free oxygen, and the air above them shared that absence. Instead, gases such as methane, carbon dioxide, and nitrogen drifted through the sky, while the seas carried dissolved iron and other minerals in abundance. Within this setting, the earliest living systems emerged, shaped entirely by conditions that lacked the element now so closely tied to animal life. Those first organisms drew energy through anaerobic pathways, reactions that required no oxygen and often could not tolerate it. Their enzymes had evolved in a world where that gas was not merely unnecessary, but reactive enough to disrupt delicate molecular structures. For them, exposure to it would have meant chemical damage, a disturbance capable of unraveling the very processes that sustained their existence. What later generations would breathe with ease would once have posed a silent hazard. Change began gradually, guided by microorganisms that harnessed sunlight in a new way. These tiny architects used light to split water molecules, releasing oxygen as a byproduct. At first, the released gas vanished quickly, binding with dissolved iron in the oceans and forming vast deposits that settled onto the seafloor. For millions of years, this absorption kept the atmosphere largely unchanged, as though the planet itself were quietly buffering the transformation. Eventually, those mineral sinks became saturated, and the excess oxygen began to accumulate in the water and air. This transition, known as the Great Oxygenation Event, altered Earth's chemistry on a global scale. Compounds stable in earlier conditions reacted and disappeared, while new substances formed in their place. Many anaerobic organisms found themselves in an environment no longer suited to their physiology. Some retreated into sediments or other protected niches where the old chemistry lingered. Others could not adjust and vanished, leaving only traces in ancient rock. The shift unfolded across immense spans of time, yet its consequences were profound. Oxygen reshaped the possibilities of metabolism, enabling reactions that released far more energy than earlier pathways allowed. Lineages capable of tolerating and eventually using it gained access to this energetic advantage, and their descendants diversified into forms increasingly complex. Meanwhile, survivors of the earlier world persisted in hidden refuges, maintaining metabolic traditions that predated the change. Through this transformation, life demonstrated an enduring flexibility. Rather than yielding entirely to new conditions, it explored multiple responses, adaptation in some branches, withdrawal in others. The atmosphere continued to evolve, its composition drifting toward the mixture familiar today, while the legacy of that ancient transition remained inscribed within cells, in enzymes that still carry the memory of a time when oxygen was a stranger to Earth's living systems. In stone layers laid down more than 500 million years ago, there appears a sudden richness of form, as though life had discovered a new language and begun speaking in many dialects at once. Fossils from this interval reveal shells, limbs, sensory structures, and body plans unlike anything preserved in older strata. This flourishing, often called the Cambrian explosion, has long been linked to a quiet transformation that preceded it, the gradual rise of oxygen in ocean and air. With more of that reactive element available, it seemed natural to imagine that cells gained the energetic surplus needed to construct larger bodies and intricate anatomies. For decades, this connection guided interpretation. Oxygen, in this view, functioned as a key that unlocked complexity, allowing tissues to specialize and organisms to expand beyond microscopic scale. Geological evidence supported the association, since chemical signatures in ancient sediments suggested that concentrations of dissolved oxygen increased not long before this diversification. The alignment of timing appeared persuasive, like two currents meeting at the same shore. Yet the deeper one looks into biology, the more gently that certainty begins to loosen. Even within modern environments where oxygen remains scarce, there exist organisms whose structures display careful organization, coordinated tissues, and distinct developmental stages. Their presence hints that complexity may not depend solely on abundance of a single gas, but on how effectively energy of any kind can be gathered and used. Oxygen offers a particularly efficient route, though efficiency is not the only path evolution can follow. Comparative studies of living species suggest that anatomical intricacy can arise under a range of chemical circumstances, provided that stability persists long enough for gradual refinement. What oxygen may have supplied during the Cambrian was not the sole spark of innovation, but an expansion of possibilities, widening the spectrum of forms that could be sustained. Where energy became easier to obtain, natural selection explored designs that would have been too costly before. Limbs strengthened, sensory organs sharpened, and movement diversified, each change supported by the increased energetic margin. This perspective does not diminish the significance of that ancient proliferation. Instead, it reframes it as one chapter in a broader narrative in which life responds to shifting conditions with whatever strategies prove workable. The rise of oxygen allowed certain lineages to flourish spectacularly, yet it did not erase alternative solutions evolving quietly elsewhere. Complexity, it seems, is less a single destination than a landscape with many routes, some bright with abundance, others sustained by subtler means. Seen in this light, the Cambrian world becomes not a sudden miracle, but a moment when environmental change aligned with biological potential, revealing forms that had long been possible but rarely expressed. Oxygen helped illuminate those possibilities, though the capacity for intricate life had deeper roots, extending into eras when the planet's chemistry followed very different rules. There are intervals in Earth's history when the fossil record grows strangely quiet, as if whole chapters were softened before they could fully set into stone. One of the most profound of these intervals occurred near the close of the Permian period, when life on land and in the sea diminished on a scale unmatched before or since. The causes unfolded gradually, guided by shifts in climate and circulation that altered the chemistry of the oceans themselves. As temperatures rose across the globe, the difference between warm surface waters and colder depths intensified. This layering reduced the natural overturning that normally carries dissolved gases downward and brings nutrient-rich water upward. Without that circulation, deeper regions began to lose their oxygen supply. Microbial processes continued consuming what remained, and with no steady renewal, vast volumes of seawater drifted toward anoxic conditions. The change did not arrive as a sudden wave, but as a slow settling, a quiet transformation spreading basin by basin. Within those depleted depths, certain bacteria found opportunity. Species capable of using sulfate instead of oxygen multiplied, drawing energy from chemical reactions that released hydrogen sulfide as a byproduct. This gas, colorless yet potent, accumulated in the water. In sufficient concentrations, it becomes toxic to many forms of life, interfering with cellular respiration and disrupting metabolic balance. Evidence preserved in ancient sediments suggests that such conditions expanded widely during this time, allowing sulfide-rich waters to approach levels inhabited by more complex organisms. Marine communities faced mounting strain as their surroundings shifted. Creatures adapted to stable oxygen supplies encountered environments where each generation inherited slightly harsher chemistry than the last. Some populations retreated toward regions that remained habitable, while others declined where they stood. Reef systems diminished, shelled animals grew scarce, and entire ecological networks unraveled as their members disappeared. On land, parallel stresses altered climates and vegetation, amplifying the disruption already underway in the oceans. Geological records hold subtle traces of these events. Layers of rock formed during this interval contain mineral signatures consistent with widespread oxygen depletion and sulfide presence. Isotopic ratios shift, pigments associated with sulfur-loving microbes appear, and patterns of extinction align with these chemical indicators. Together, they form a mosaic of evidence that points to a world where the balance of dissolved gases had tipped far from its former state. From such distant episodes comes a quiet instruction written not in words but in patterns. The chemistry of oceans and atmosphere can change, and when it does, life responds according to its capacity to adapt. Some lineages endure by adjusting their physiology or habitat, while others fade as conditions move beyond their limits. The story preserved in those ancient strata shows that the relationship between organisms and their environment is neither fixed nor permanent, but a continuing exchange shaped by forces that operate across immense spans of time. In the far reaches below the sunlit surface, time seems to loosen its grip, stretching each moment into a longer span than it would hold elsewhere. Temperature plays a quiet role in this transformation. Water near the seafloor hovers just above freezing, and within such cold surroundings, chemical reactions proceed with deliberate restraint. Molecules move more slowly, enzymes shift shape at a gentler pace, and the metabolic rhythms that sustain life settle into extended intervals. What might occur in seconds in warmer habitats may require minutes here, and processes that once filled days can unfold across years. This measured tempo shapes every aspect of existence. Creatures that inhabit these depths do not rush in search of nourishment, for nourishment itself is rare. Most organic matter arrives only after drifting downward from distant layers above, descending as faint particles or occasional larger fragments. Between these infrequent offerings lie long stretches of absence. To endure such scarcity, animals adapt by lowering their demands, maintaining bodies designed for efficiency rather than speed. Muscles remain modest, tissues sparse, and movement purposeful rather than constant. Behavior follows the same principle. Some species remain motionless for extended periods, conserving energy until a passing current carries sustenance within reach. Others travel slowly across the seabed, guided by chemical cues too subtle for hurried pursuit. Even predation occurs with patience, the hunter relying on stillness as much as pursuit. In this environment, restraint becomes a form of strength, allowing survival where restless activity would exhaust precious reserves. Longevity often accompanies this unhurried life. Certain deep-dwelling organisms grow so gradually that individuals may persist for decades or even centuries. Their cells divide infrequently, their tissues repair themselves with care, and their overall aging proceeds at a pace aligned with their surroundings. Time leaves marks upon them, yet those marks accumulate slowly, like faint lines traced across stone by a gentle current. The dominance of conservation over expenditure defines these communities. Energy is treated not as something to be spent freely, but as a resource to be guarded, allocated only when necessary. Internal systems reflect this philosophy, with metabolic pathways tuned to extract the greatest possible value from each morsel consumed. Even reproduction may occur at wide intervals, timed to coincide with moments when conditions offer slightly greater abundance. Such lives unfold according to a clock set not by daylight or seasons, but by chemistry and cold. In that quiet realm, existence continues at a pace almost imperceptible to observers accustomed to swifter worlds, yet fully suited to the steady stillness that surrounds it. Beneath the visible surface of the seabed lies another landscape, one not shaped by ridges or valleys, but by layers of compacted grains descending into darkness. Each stratum holds a population of organisms so small that their presence escapes ordinary sight, yet together they form communities that extend meters below the ocean floor. These sediments are not inert deposits. They are habitats structured by gradients of chemistry that shift subtly with depth, creating distinct zones where different forms of life persist. Near the upper layers, where traces of dissolved compounds filter downward from the water above, microbes gather that can make use of these faint supplies. They metabolize organic remnants that settle from distant waters, breaking complex molecules into simpler fragments. As depth increases, those resources change, and with them, the inhabitants. Oxygen is absent, yet other substances take its place as partners in metabolism. Microorganisms adjust accordingly, each group specialized for the particular chemistry surrounding it. Among the most remarkable residents are those that produce methane. These archaea, adapted to extreme conditions, generate energy by combining hydrogen with carbon compounds, releasing methane as a final product. Their activity unfolds slowly, often at temperatures near freezing and under pressures that would halt most biochemical reactions. Even so, they persist, converting minute quantities of material into gas that may remain trapped within the sediment or drift upward over long spans of time. Their presence links deep geological processes with the living world, bridging realms once thought separate. Sharing this hidden domain are sulfate-reducing bacteria, organisms that draw energy by transforming sulfate into sulfide. In doing so, they participate in a cycle that recirculates elements through the sedimentary environment. The compounds they produce influence the surrounding chemistry, shaping which other microbes can survive nearby. These interactions form networks as intricate as any visible ecosystem, though their participants measure only micrometers across. The deeper one descends into these buried layers, the slower life proceeds. Nutrients become scarce, and cell division may occur only after months or years. Some microorganisms remain viable for astonishing lengths of time, their metabolic activity reduced to levels barely detectable. They endure not through speed or abundance, but through stability, maintaining their internal processes with extraordinary efficiency. In such conditions, a handful of cells can sustain a lineage across geological intervals. Though unseen, this subsurface biosphere spans vast regions beneath the ocean floor, rivaling the scale of more familiar habitats. It forms a quiet foundation for planetary chemistry, influencing cycles of carbon, sulfur, and other elements that shape the environment above. Within these buried layers, life continues its patient work, threading through grains of sediment in a realm where motion is minimal and persistence defines existence. Across recent decades, long records kept by oceanographers have begun to show a subtle yet persistent trend, a quiet thinning in the amount of dissolved oxygen held within seawater. The change is not uniform, nor does it announce itself with spectacle, yet its pattern appears again and again in measurements drawn from distant regions. Instruments lowered into the depths return with profiles that reveal slightly diminished concentrations compared with those taken in earlier years, as though the ocean's vast reservoir of breath were slowly easing downward. One cause lies in the warming of the surface layers. As water absorbs heat from the atmosphere, its capacity to retain dissolved gases declines, a property governed by physical laws that operate regardless of location. Warmer molecules move more vigorously, allowing oxygen to escape more readily back into the air. At the same time, heating strengthens stratification, creating more stable layering that limits exchange between upper and lower depths. Without regular mixing, oxygen absorbed near the surface remains there, while deeper zones receive less renewal. Marine communities respond in gradual ways to these shifts. Species that depend on steady supplies adjust their ranges, inhabiting narrower bands where conditions remain suitable. Fish that once occupied broad vertical territories now concentrate within thinner layers, their movements guided by the chemistry surrounding them. Such compression can alter feeding patterns, bringing predators and prey into closer proximity and changing relationships that have persisted for generations. Fisheries sometimes register these changes as variations in catch, depth, or abundance, subtle signals of a larger transformation unfolding below. Organisms adapted to low oxygen may find new opportunities as these regions expand. Creatures already equipped for scarcity can persist where others withdraw, their physiological traits suited to environments that are becoming more common. This does not occur as a sudden replacement, but as a gradual adjustment in community composition, with tolerant species occupying spaces that once supported more demanding forms. The balance of marine ecosystems shifts accordingly, shaped by differences in metabolic need. Chemical records preserved in seawater samples confirm that these patterns align with broader climatic trends. Rising global temperatures influence circulation, stratification, and solubility all at once, linking atmospheric change to conditions beneath the waves. Each factor contributes incrementally, yet together they guide a measurable alteration in the distribution of oxygen throughout the oceans. Within this unfolding process lies a reminder written in the language of chemistry and biology together. The availability of a single element can influence entire networks of life, determining where organisms thrive, where they retreat, and how communities assemble. As conditions continue to evolve, the living fabric of the sea adjusts in response, its structure reshaped by forces that operate quietly but persistently across the modern world. Far from shorelines and storms, vast currents move through the ocean with a steadiness that belies their importance. These flows travel across basins and descend through depths, carrying dissolved gases along paths shaped by temperature and salinity. Through their motion, oxygen absorbed at the surface is conveyed into darker layers, where it becomes available to organisms that would otherwise find none. The process unfolds without sound or spectacle, a continuous circulation that links distant regions into a single breathing system. This exchange depends on delicate balances. When surface water cools or grows saltier, it becomes denser and sinks, drawing upper layers downward while allowing deeper water to rise in its place. Such overturning renews the chemical composition of entire columns, distributing oxygen and nutrients with quiet regularity. Even small differences in temperature or salinity can alter this behavior, because density responds to both with subtle sensitivity. The ocean's structure is therefore not fixed but poised, maintained by conditions that must remain within certain bounds. As warmth increases, that balance shifts. Slight heating reduces density at the surface, making it less likely for upper water to sink. The layers become more distinct, forming a stratified arrangement that resists vertical motion. Once established, this separation limits the downward transport of oxygen, leaving deeper regions dependent on what they already contain. Over time, respiration and chemical reactions consume that supply, gradually changing the composition below. The chemistry responds quietly to these adjustments. Reactions that require oxygen slow or cease, while others that proceed without it begin to dominate. Dissolved substances accumulate or diminish according to these new pathways, altering the environment for organisms adapted to previous conditions. Because the system operates as an interconnected whole, a modest shift in temperature at the surface can influence processes occurring far beneath, linking atmosphere and abyss through chains of cause and effect. Scientists sometimes describe such systems as approaching thresholds, not as abrupt edges but as ranges beyond which behavior changes more quickly. Within certain limits, circulation persists and maintains equilibrium. Beyond them, stratification strengthens, mixing weakens, and chemical gradients sharpen. The transition need not be dramatic to be significant. A difference of fractions of a degree can adjust density enough to alter the motion of entire water masses. This sensitivity reveals how finely tuned the ocean's internal movement remains. Its currents depend on contrasts that are slight yet essential, sustained by the balance of heat, salt, and gravity acting together. When those contrasts shift, the patterns of circulation respond, and with them the distribution of oxygen that countless forms of life rely upon. In this way, the vastness of the sea rests upon relationships so subtle that their influence can be traced to the smallest variations in temperature and composition. Size carries a quiet price in the living world, one paid not in sound or motion but in energy. As bodies grow larger and more intricate, their cells require a steady stream of fuel to maintain structure, coordinate activity, and repair the constant wear of existence. For most animals, this demand is met through reactions that rely on oxygen, whose presence allows nutrients to be broken down completely and efficiently. The result is a generous yield of chemical energy, sufficient to support tissues that must work continuously. Among the most demanding of these tissues are muscles and nervous systems. Muscle fibers consume energy each time they contract, even in the smallest movement, while nerve cells expend it to maintain electrical gradients and transmit signals across delicate membranes. In animals with complex behavior, these processes operate without pause, sustaining perception, response, and motion from one moment to the next. Such activity requires a dependable supply, and oxygen-based metabolism provides it with remarkable consistency. When that supply is absent or scarce, different rules apply. Cells must rely on alternative pathways that release only modest amounts of energy, enough for maintenance but rarely enough for sustained exertion. Under these conditions, elaborate organs become difficult to support. A large brain, with its dense network of signaling cells, would demand more energy than such chemistry can furnish. Extensive musculature would likewise exceed the available budget. The architecture of life adjusts accordingly, favoring forms that remain small and structurally simple. In environments where oxygen is limited, this constraint shapes evolution over long spans. Organisms that persist there tend toward minimalism, their bodies streamlined to match the modest energy flow they can obtain. Tissues remain thin. Internal transport relies on diffusion rather than active circulation, and growth proceeds slowly. These features are not signs of deficiency, but expressions of balance. each one aligned with the conditions surrounding it. The contrast with more complex animals highlights how closely form follows energy. Creatures possessing skeletons, elaborate sensory organs, or rapid movement invest heavily in the metabolic processes that sustain those traits. Their complexity grants advantages in perception and interaction, yet it also binds them to environments where sufficient oxygen is present. Without that support, their intricate systems would falter. Thus, the boundaries of multicellular design are drawn not only by genetics or time, but by the chemistry that fuels every cell. Where energy is abundant, life explores elaborate possibilities. Where it is scarce, it turns towards simplicity, refining structures that can endure on less. The smallest inhabitants of oxygen-poor realms embody this principle, their scale reflecting a careful equilibrium between ambition and supply, between what biology might attempt and what chemistry can sustain. Within living cells, oxygen participates in reactions that release remarkable stores of energy, yet its presence carries a quiet tension. The same chemical qualities that make it so effective at drawing electrons also render it capable of forming reactive byproducts. As metabolism proceeds, small fractions of oxygen are converted into unstable molecules known as reactive oxygen species. These fleeting compounds can interact with proteins, membranes, and genetic material, altering their structure if not carefully controlled. Cells have evolved intricate systems to manage this double-edged chemistry. Enzymes such as superoxide, dismutase, and catalase intercept reactive molecules, transforming them into less harmful forms before they can accumulate. Antioxidant compounds circulate within tissues, acting as buffers that absorb excess reactivity. Even the architecture of cellular compartments reflects this vigilance, with sensitive processes separated from regions where oxygen is most active. Through these layered protections, life harnesses the energetic advantages of oxygen while limiting its disruptive potential. The need for such balance shapes metabolism at every scale. When oxygen levels rise, energy production can increase, yet so does the likelihood of oxidative damage. When levels fall, risk diminishes, though energy becomes scarce. Organisms therefore regulate how quickly they use oxygen, adjusting respiration rates, altering enzyme activity, or modifying behavior to keep internal conditions within tolerable bounds. This regulation resembles a quiet negotiation between benefit and hazard, conducted continuously within each living cell. Across evolutionary time, this negotiation has guided adaptation. Some species have developed robust antioxidant defenses that allow them to function in environments rich in oxygen, supporting active lifestyles and complex structures. Others have reduced their reliance on oxygen, favoring pathways that generate less energy but also produce fewer reactive byproducts. Each strategy reflects a different compromise, shaped by surroundings and ancestry alike. The chemistry of oxygen thus presents both opportunity and constraint. Its ability to accept electrons makes it an efficient partner in metabolism, yet that same property requires careful oversight. Life responds not by rejecting it or embracing it without limit, but by integrating it into systems of regulation that maintain stability. Within those systems, molecules are passed along controlled routes, enzymes stand ready to neutralize excess reactivity, and cellular conditions are kept within ranges that permit function without harm. Through this continual balancing act, organisms transform a potentially destructive substance into a reliable source of vitality. The relationship remains dynamic rather than fixed, sustained by countless microscopic adjustments that unfold from moment to moment. In that ongoing exchange, Oxygen serves as both benefactor and challenge, a presence whose value depends on the precision with which it is handled. Beyond Earth, many worlds drift through space, wrapped in atmospheres and oceans unlike our own, their chemistries shaped by distances from the sun and by histories written in ice or stone. For a long time, the search for life among them focused on the presence of oxygen, since on this planet it accompanies complex organisms so reliably. Yet the study of Earth's most unusual habitats has begun to soften that expectation, suggesting that intricate living systems might arise even where that familiar gas remains scarce or absent. Moons orbiting distant planets offer examples that invite such reflection. Beneath the frozen crust of Europa, evidence points to a vast ocean concealed under kilometers of ice. Sunlight does not penetrate there, and any oxygen produced at the surface would struggle to reach the depths below. Still, chemical reactions between water and the moon's rocky interior could supply alternative sources of energy, forming gradients capable of sustaining metabolism. In such an environment, life would not depend on atmospheric exchange, but on interactions between mineral and liquid, drawing power from processes that unfold slowly yet persistently. Farther outward lies Titan, where lakes and seas consist not of water but of liquid hydrocarbons. Its surface temperature rests far below the freezing point familiar to terrestrial biology, and its atmosphere contains abundant methane and nitrogen rather than oxygen. Though conditions differ profoundly from those of Earth, the presence of stable liquids and complex organic molecules raises the possibility that unfamiliar biochemical systems could operate there. Any organisms adapted to such surroundings would rely on reactions suited to their environment, perhaps using compounds that on Earth serve only minor roles. These possibilities broaden the concept of habitability. Instead of requiring a single chemical ingredient, life may emerge wherever energy flows steadily and matter can assemble into organized structures. Oxygen remains one pathway among many, powerful but not exclusive. The diversity already observed in Earth's hidden ecosystems shows how biology can align itself with varied conditions, adopting strategies that match the resources available. Planetary scientists now consider a wider range of environments when evaluating distant worlds. They examine temperature, pressure, solvent presence, and chemical disequilibria, searching for combinations that could sustain persistent reactions. In this view, habitability becomes less a narrow doorway and more a landscape of potential niches, each defined by its own balance of physics and chemistry. Through this expanding perspective, the universe appears less constrained in its possibilities. Worlds once dismissed as inhospitable may instead hold quiet regions where life could endure, shaped by principles that echo those found in Earth's most secluded habitats. The realization does not promise that such life exists, yet it suggests that the conditions supporting it may be more varied than once imagined, extending the reach of biological potential across environments both familiar and profoundly different. Lowering instruments into the deepest reaches of the ocean requires a kind of patience that mirrors the stillness of the environment itself. Research vessels position themselves with careful precision, guided by satellite signals and seafloor maps, then release mechanical explorers designed to descend through kilometers of water. These remotely operated vehicles travel slowly downward, their lights cutting narrow paths through the dimness, their movements controlled from far above by quiet commands transmitted along fiber optic cables. When they reach the seabed, their mechanical arms begin work that must be performed with extraordinary delicacy. One of their primary tasks is the collection of sediment cores, slender columns of layered material extracted intact from the seafloor. The sampling devices are engineered to slide into the sediment with minimal disturbance, sealing the sample before it can mix with surrounding water. Inside each core lies a vertical record of chemical and biological history, arranged in thin bands that correspond to gradual deposition over long spans of time. Alongside these physical samples, instruments measure the surrounding chemistry directly. Sensors detect concentrations of dissolved gases, acidity, temperature, and trace compounds, transmitting continuous streams of data to the surface. Each reading provides a snapshot of conditions at a specific depth, allowing researchers to map subtle gradients that would otherwise remain undetected. Because these gradients can shift within mere centimeters, the instruments must be calibrated with exceptional precision, capable of registering changes so slight they would escape ordinary observation. Maintaining purity during collection is essential. Any intrusion from upper layers or from the research equipment itself could alter the delicate balance within a sample. To prevent this, tools are sterilized before descent, and sealed compartments isolate the collected material until it reaches controlled laboratory spaces aboard the vessel. Even the handling of the cores follows strict procedures, with scientists wearing protective gear and working within enclosed stations that limit exposure to outside air. These precautions ensure that what is studied reflects the original environment rather than accidental contamination. The challenges of such work extend beyond technique. Depth exerts immense pressure on equipment. Cold temperatures affect mechanical performance, and communication delays complicate control of remote vehicles. Each expedition must account for these factors, designing instruments capable of withstanding conditions that strain both materials and electronics. Repairs or adjustments cannot be made once a vehicle has descended, so reliability must be built into every component before launch. Despite these difficulties, the effort reveals environments otherwise beyond reach. Through careful sampling, precise measurement, and rigorous safeguards, scientists reconstruct the hidden characteristics of deep sediments without disturbing their fragile balance. The process unfolds slowly, guided by steady attention and meticulous design, allowing knowledge to rise from the depths as gently as the cores themselves ascend toward the waiting light above. Acceptance in science rarely arrives all at once. Even the most careful observations must pass through a period of quiet examination, during which evidence is weighed, methods are reviewed, and interpretations are tested against other possibilities. When reports first described complex organisms inhabiting sediments thought incapable of supporting them, the response among researchers unfolded with measured caution. The claim did not provoke dismissal so much as deliberate scrutiny, a process shaped by the understanding that extraordinary findings require equally steady confirmation. Skepticism formed naturally from long-held principles. For generations, biological theory had linked multicellular life with dependable access to oxygen, not as a casual association but as a pattern supported by countless studies. The suggestion that certain animals might complete their existence without it seemed to stand apart from this framework. Scientists reading the reports examined the data closely, looking for overlooked variables or hidden sources that could account for the observations without overturning established expectations. One possibility considered was contamination during sampling or analysis. Because the specimens had been retrieved from extreme depths using complex equipment, even slight intrusion from upper layers or from the machinery itself might introduce organisms not native to the original environment. Researchers therefore studied collection procedures, storage conditions, and laboratory handling, assessing whether any stage might have allowed foreign material to enter. Such questions did not imply error, but reflected the discipline's commitment to tracing every result back to its origin. Replication posed another challenge. The environments in question are difficult to reach, and opportunities to gather new samples are limited by time, resources, and the technical demands of deep exploration. Without multiple independent collections confirming the same findings, conclusions must remain provisional. Teams planning additional expeditions worked to refine techniques, seeking to reproduce the original conditions as closely as possible, so that new evidence could be compared reliably with earlier results. Alternative explanations continued to circulate as well. Some investigators suggested that the organisms might endure only temporarily in those sediments, surviving in dormant states rather than completing full life cycles there. Others proposed that subtle chemical gradients might exist within the habitat, providing minute traces of oxygen sufficient for survival. Each hypothesis prompted further measurements and analyses, adding layers of detail to the unfolding discussion. Through this gradual exchange of ideas, the scientific conversation extended across journals, conferences, and laboratories. Rather than reaching a swift verdict, understanding advanced through accumulation, each new dataset contributing another piece to the picture. The debate itself became part of the process, a steady dialogue shaped by evidence and revision. In this way, controversy functioned not as conflict but as refinement. Careful doubt ensured that interpretations rested on solid ground, and continued investigation allowed knowledge to grow with patience. The discovery remained under consideration, held within a thoughtful balance between possibility and proof, as inquiry moved forward with the same deliberate rhythm that guides so many processes in the natural world. Strength in the living world is often imagined as motion or force, yet in certain hidden environments, it takes a quieter form. There, survival does not belong to the swift or the large, but to those whose needs are small enough to be met by what little is available. Organisms shaped by such conditions do not strive to outrun rivals or overwhelm their surroundings. Instead, they endure, sustaining themselves through careful use of energy that arrives only in faint and intermittent supply. Their physiology reflects this principle of restraint. Every cellular reaction proceeds with measured economy, extracting as much value as possible from each molecule encountered. Structures remain simple, not through limitation but through refinement, as complexity would demand more energy than the environment can provide. In such bodies, efficiency replaces extravagance, and balance replaces excess. The result is a form of vitality that depends less on abundance than on precision. This way of life alters the meaning of success. Rather than spreading rapidly or occupying vast territories, these organisms persist in the same place across long spans of time. Their presence may remain unnoticed, yet it continues without interruption, generation following generation. While more active species rise and decline with changing conditions, these quieter inhabitants maintain their steady course, their stability rooted in modest requirements that rarely exceed what their surroundings can supply. Even competition assumes a different character in such settings. When resources are scarce, aggressive growth offers little advantage, since expansion would only increase demand. Selection, therefore, favors those that conserve rather than consume, those that maintain internal harmony instead of pursuing rapid gain. Over many generations, this preference shapes populations whose defining trait is not dominance but durability. From a distance, such organisms might appear fragile, their small forms lacking the defenses or speed associated with strength, yet their persistence tells another story. They withstand fluctuations that would challenge more demanding life, remaining viable through shifts in chemistry and supply. Their resilience arises from alignment with their environment, a close correspondence between what they require and what is available. Because they ask so little, they can continue where others cannot. This pattern offers a broader reflection on the nature of endurance. Life does not always prevail through intensity or scale. Sometimes it endures through quiet adjustment, through designs that fit so precisely within their conditions that disruption rarely dislodges them. In these understated survivors, strength reveals itself as patience, a steady continuity, sustained not by force, but by the art of existing within limits, between grains of sediment or within layers of water that appear uniform to the eye. There exist borders too fine to be seen, yet precise enough to define entire habitats. These boundaries are drawn not by walls or surfaces, but by chemistry itself. Dissolved substances vary in concentration from one point to another, forming gradients that shift gradually across distances smaller than a fingertip. To larger creatures, such differences would seem negligible, though to microscopic life, they mark distinct regions as clearly as shorelines divide land from sea. Within a single teaspoon of marine sediment, oxygen may be present near the top while absent just a few millimeters below. Sulfide may accumulate in one layer, nitrate in another, each compound occupying its own narrow band according to the reactions occurring there. The arrangement resembles a vertical mosaic, assembled from molecules rather than stone, every piece shaped by the balance between diffusion, consumption, and chemical transformation. These zones remain stable so long as the processes that create them continue in equilibrium. Life responds to these gradients with remarkable specificity. Certain microbes thrive only where sulfate concentrations reach a particular range, while others gather where methane seeps upward from deeper strata. Some organisms position themselves exactly along the boundary between two chemical conditions, drawing resources from both sides at once. Their distribution forms delicate patterns, colonies aligned with invisible contours that trace the underlying chemistry of their surroundings. The scale of these environments invites a different sense of geography. Instead of continents and oceans, there are layers and pockets measured in fractions of centimeters. A shift of a few grains can move an organism from one chemical regime into another entirely. Because of this, even slight disturbances, a passing current, a settling particle, or the movement of a neighboring creature can reshape the local arrangement and alter which forms of life can persist there. Such hidden architecture arises from fundamental physical laws. Molecules diffuse from areas of higher concentration toward lower ones, while biological activity modifies those concentrations through metabolism. The interplay of these forces produces stable gradients that endure as long as inputs and reactions remain balanced. In this way, chemistry sculpts an unseen landscape, guiding the distribution of organisms as surely as terrain guides travelers. Though invisible, these boundaries exert profound influence. They determine where energy can be obtained, which reactions are possible, and how communities assemble. Each gradient acts as a quiet organizer, structuring ecosystems without any visible sign of its presence. Within this subtle framework, life adapts with extraordinary precision, aligning its processes to the contours of an environment defined not by shape or color, but by the silent arrangement of molecules. Ideas about the natural world often begin as quiet certainties, shaped from careful observation and repeated testing until they feel as steady as stone. For long stretches of time, they guide understanding without challenge, forming the framework through which new discoveries are interpreted. Yet history shows that such frameworks can shift, not abruptly, but through gradual refinement as evidence accumulates. When new findings appear that do not fit comfortably within established patterns, they invite reconsideration, encouraging knowledge to adjust its outlines. Science has passed through many such revisions. Continents once thought fixed were found to drift slowly across the globe. Invisible microorganisms, unknown to earlier observers, revealed themselves as essential participants in health and ecology. Even the nature of light, long debated, came to be understood as both wave and particle, depending on how it is examined. Each transformation did not erase what came before, but extended it, showing that earlier conclusions were steps along a longer path rather than final destinations. The study of life offers similar moments of expansion. Organisms discovered in unusual habitats have repeatedly broadened the range of conditions once believed necessary for survival. Environments once dismissed as barren have proved to host intricate communities, their existence revealed through instruments capable of detecting what unaided senses cannot perceive. With each such finding, the definition of what counts as habitable space grows more inclusive, shaped less by assumption and more by observation. This pattern fosters a particular quality within scientific practice, a willingness to hold conclusions with care rather than finality. Researchers learn to regard even well-supported ideas as open to revision should new evidence arise. Such openness does not weaken understanding. Instead, it strengthens it, ensuring that explanations remain aligned with the natural world rather than fixed by expectation. In this way, uncertainty becomes not an obstacle but a guide, pointing toward questions that merit closer attention. The recognition that knowledge can evolve also brings perspective. Discoveries that challenge established views do not diminish earlier work, for those earlier efforts provided the tools and concepts that made new insight possible. Progress unfolds as a continuous conversation across generations, each contribution refining what is known and clarifying what remains to be explored. Through this process, understanding deepens gradually, like a lens brought into finer focus. Within that ongoing dialogue, humility becomes an integral companion to curiosity. The natural world is vast, its patterns intricate, and any single explanation captures only part of its complexity. By remaining attentive to evidence and receptive to revision, science preserves its ability to grow. Each unexpected observation, rather than closing inquiry, opens it further, reminding us that even the most familiar principles may hold subtleties yet to be seen. Long before written records or fossils pressed into stone, the seafloor began its quiet work of keeping history. Particle by particle, it gathers what drifts down from above, storing fragments of shells, minerals, and organic remains in thin accumulating layers. Each addition settles gently atop the last, forming a stratified archive that deepens with time. Unlike landscapes shaped by wind or weather, these submerged deposits can remain undisturbed for immense spans, preserving traces of conditions that once prevailed at the surface and throughout the water column. Within those layers, chemistry lingers as a record. Ratios of elements, isotopic signatures, and mineral forms reflect the composition of ancient oceans, capturing shifts that occurred long before observers existed to witness them. By studying these patterns, researchers can infer changes in temperature, nutrient availability, and atmospheric influence across geological eras. The sediments do not speak in words, yet their structure holds a chronology written in molecular language, each band corresponding to a chapter in Earth's unfolding story. Embedded within this archive are signs of early living systems. Microscopic impressions, fossilized cell walls, and chemical residues left by metabolism offer glimpses of organisms that inhabited the planet when its environment differed greatly from today. Some layers contain biomarkers, distinctive compounds produced only by certain biological processes, which persist long after the organisms themselves have vanished. These molecules function as faint signatures, indicating which forms of life once flourished and what conditions supported them. The deeper the sediment, the older the memory it contains. Pressure compacts the lower strata, sealing them from disturbance and slowing chemical alteration. In such protected zones, delicate structures can remain recognizable across astonishing durations. Scientists extracting cores from these depths read them from top to bottom as one might read a chronicle, tracing transitions from recent eras into epochs so distant that continents and climates bore little resemblance to their modern forms. This preservation grants insight into periods when Earth's atmosphere and oceans differed profoundly from those familiar now. Variations in mineral composition can reveal intervals when certain gases were scarce or abundant, while shifts in fossil assemblages mark transitions in biological communities. By aligning these clues, a picture emerges of how planetary conditions and living systems have influenced one another through time, each shaping the other in a long and intricate partnership. Such records remind us that the deep sea is not only a habitat, but also a repository. Its sediments hold evidence of vanished worlds, safeguarding information that might otherwise have been lost to erosion or tectonic change. Through careful study, these quiet layers yield knowledge about ancient chemistry and early biology, allowing the distant past to be examined with surprising clarity. In their stillness, they preserve a continuity that stretches across ages, linking present understanding to origins that lie far beyond direct memory. Not all existence announces itself with movement or sound. In many corners of the living world, presence is marked instead by continuity, by the simple fact that something remains where conditions allow it to remain. Such life does not rush or display. It endures quietly, maintaining its processes with such subtlety that its activity can pass unnoticed even while it continues uninterrupted. This form of persistence arises where resources arrive slowly and unpredictably. Organisms shaped by such surroundings adjust their rhythms until they match the pace of what is available. Growth unfolds gradually, sometimes over spans so long that change becomes almost imperceptible. Cells divide at intervals measured not in hours or days but in extended cycles, each division a careful investment of energy gathered piece by piece. In this way, time itself becomes an ally, allowing survival through moderation rather than haste. Stillness can serve as protection as well. Motion requires expenditure, and in habitats where supply is limited, restraint preserves strength. Many inhabitants of these regions move only when necessary, conserving their reserves for essential functions. Their quietness is not inactivity but strategy, a deliberate alignment between behavior and circumstance. By avoiding unnecessary effort, they remain prepared for moments when action is required. Reproduction follows a similar pattern of patience. Instead of producing vast numbers of offspring at once, some species release them sparingly, timing each generation to coincide with brief intervals of favorable conditions. Others form durable stages capable of withstanding long periods until surroundings shift in their favor. Such approaches emphasize reliability over abundance, ensuring continuity even when opportunity is rare. To an outside observer, These forms of life might appear absent simply because they draw little attention. Their presence is written in traces rather than spectacle, in chemical signatures, microscopic structures, or faint alterations to their surroundings. Yet these subtle indicators reveal systems that have persisted through cycles of change, remaining stable while more conspicuous communities rise and fade. This quiet endurance reflects a broader principle woven throughout biology. Survival does not always depend on rapid response or visible dominance. Sometimes it depends on remaining balanced within narrow limits, maintaining internal harmony despite fluctuations beyond. In such cases, success belongs to those whose needs are modest and whose processes remain steady. Across vast stretches of time, this gentle persistence shapes ecosystems in ways that may never be obvious at a glance. Layer upon layer, generation upon generation, life continues its work without proclamation. The effect is cumulative, a slow weaving of continuity that binds past to present. Within that steady unfolding, existence proves that vitality can reside in calmness, and that endurance often speaks most clearly through silence. Far beneath the last traces of daylight, the seafloor settles into a realm governed not by wind or weather, but by reactions unfolding molecule by molecule. Here, chemistry shapes existence the way climate shapes landscapes elsewhere, determining what can persist and how. In these depths, energy does not arrive in bright bursts. It seeps through mineral exchanges and gradual transformations, sustaining forms of life adapted to conditions that would seem austere by surface standards. Within such places, oxygen no longer stands as the central currency of survival. Its absence does not halt all processes, nor does it render the environment empty. Instead, other elements assume roles usually attributed to it, accepting or donating electrons in slow metabolic cycles. These pathways yield modest returns, yet they provide enough for organisms whose structures and rhythms are tuned to minimal demand. In their cells, reactions proceed with careful efficiency, sustaining function without excess. The surroundings themselves appear almost unchanged across long intervals. Particles drift downward from distant waters and settle gently, adding to deposits that accumulate grain by grain. Each addition becomes part of a stable foundation where movement is rare and disturbances are slight. Such steadiness allows fragile arrangements to remain intact, preserving both chemical patterns and the organisms that depend on them. In this stillness, time seems to lengthen, stretching moments into spans that allow even the faintest processes to continue. These hidden regions reveal that the ocean contains not one continuous environment, but many, layered and varied, each defined by its own balance of substances. Some zones support creatures that rely on familiar reactions, while others host communities whose metabolisms follow less common routes. Together, they form a mosaic of habitats extending across the seafloor, each quietly demonstrating that life can adjust to circumstances once thought beyond its reach. The realization does not arrive with spectacle. It emerges gradually through observation as careful study uncovers patterns that had long remained concealed. With each discovery, understanding widens slightly, acknowledging that vitality can persist under conditions very different from those once considered necessary. The lesson rests not in surprise but in recognition, a gentle shift in perspective shaped by evidence gathered from places few have seen. Down there, beneath layers of water and time, existence continues at its own measured pace. It does not rush or proclaim its presence. It endures through balance, through alignment with its surroundings, through the quiet continuity of processes that require little yet accomplish enough. In that deep stillness, life remains, not dramatic, not loud, simply present, sustained by the subtle forces that shape the most silent corners of Earth.